So let's start off with your question. The homework assignment says that it's due on Wednesday. And what that means is that on Wednesday in class, you should have it worked, and then we go over it during class. And then you have the option, the ability to correct it before you turn it in on Friday. So the due date is set for Friday on Blackboard because then it allows you to upload it by that due date. But I put the due date on there to remind you of when we're going to go over it in class and talk about it. And you should, again, work it by then. It's however you want to look at it when we go over it in class. All right, that makes sense to everybody? Okay, so today we're talking about chapter 3, which is the standard atmosphere. So remember in one of the problems where we did the ideal gas, we said we were at sea level and we used a standard number for the pressure at that altitude. So this is where that information comes from. I forgot to turn the projectors on. Does it look like that one's coming on? Look in the, yeah. All right, should be coming in. Are we seeing anything on the screen?
No.
Still not seeing anything. Well, we may have to go without the screens. Everybody can see the blackboard okay? Or you can look at it on Zoom. Let me try one more time, then I'll give up. All right, so we're good. We're looking at the blackboard. So, standard atmosphere. The pressure, density, temperature vary with altitude. We know that because we sent balloons up in the atmosphere and we can see the pressure goes down, the density goes down. There's less air until you get into space and there's no air up there. Also varies with location. On the globe, if you're in Hawaii, it's warmer most of the year than it is, say, at the North Pole. Time of day, weather. So with all these, things vary. And so if we're saying, well, an airplane's flying at 10,000 feet, and we want to analyze it there, what temperature, what pressure do we use? So a long time ago, somebody defined what's called the standard atmosphere. And it's average conditions. And this was done as an NACA. We talked about what that means, National Advisory Committee on Aerodynamics, in 1925. And then it was extended to higher altitudes. In 1959, which was related, then that's the start of the space flight. So this table that we're going to use are in your textbook in Appendix A and B. So if you open up your textbook, go all the way to the back. There's two appendices. There's Appendix A, which is metric in kilometers and meters, and then Appendix B, which is in English units. All right, so all of this is, well, what does the atmosphere look like? Standard atmosphere at altitude. So we're still going to say it's going to vary with altitude. So let's talk about altitude for a minute. So okay if I erase over here? Is anybody still working on this? We're good? So here's the Earth. There's the center of the Earth. And the Earth has a certain radius. And so if we're up here a certain height above the Earth, we either have absolute altitude, which is the distance all the way up there from the center of the Earth. And we know if we're calculating gravitational effects, like for a satellite, you want to know, well, how far is it from the center of mass of the Earth? But then when we're talking about airplane flight, we're talking about altitude, geometric altitude, which is how far you are above sea level, which is what we call zero. So HA is absolute altitude, and HG is geometric altitude. And of course, the absolute altitude is going to be the geometric plus the radius of the Earth. So when we're talking about space flight or talking about airplanes, we're usually talking about this, the altitude above sea level, because that's where the air starts at sea level. We may or may not, and we'll talk about this in a bit, include the fact that gravity changes with altitude. In fact, gravity gets less and less as you get further and further away from the center of the Earth. So that may become important, and we'll talk more about this later, but I want to mention this now so that you remember that. But let's talk through, well, what is altitude as far as a couple of examples. Let's start over here. So I looked up the altitude of some places. So Tampa is pretty close to sea level, right? So if you look up its altitude, it's 27 feet. Okay, makes sense. How about Wichita? 2,500 feet. So I looked up mid-continent. Yeah, it depends on where you are in the state. If you're in Wichita at Mid-Continent Airport, I think this is runway 01 left. You're at 1,397 feet. You got to, what's the highest point in Kansas? Do you guys know that? Anybody grew up in Kansas? Mount Sunflower, right? It's all the way in the west. It's not really a mountain. It just means that the altitude keeps going up as you drive toward Denver. It's like 4,000 feet, I think. Denver, what's the altitude in Denver? About a mile high, right? That's why the Denver Broncos Stadium is called Mile High Stadium. So we're talking 5,270 feet, and then you go up into the mountains. Running out of room. Breckenridge, the town of Breckenridge, it's a ski town. It's at 9,534 feet. And then if you go to Peak 8, the double Black Diamond Bowls, that I've never skied because I'm not good enough, 12,998 feet. We know the density goes down as you go up there, right? Because it's a lot harder to breathe when you're way up on the top of the mountain. If you go all the way to the top of Pikes Peak, Pikes Peak is what's called a 14er because it's over 14,000 feet. So it's even higher. Mount McKinley, I lost the C. Mount McKinley is 20,320 feet. And then Everest is at 29,028 feet. Pretty high. Need more room, so let's go over here now. All right, how about a 747, a Boeing, in cruise? You guys have all flown, right? The captain comes on the loudspeaker and says, we have now reached our cruising altitude of, and what's it usually? 30, 31, 32,000. So the Boeing typical cruise might be 30. What'd you say? Like 33, 34,000 feet. Look at the altitude of this relative to the top of Mount Everest. It's pretty close, isn't it? I read a book a while back about climbing Mount Everest, and they talked about how if you or I were instantly transported from here right now to the peak of Mount Everest, in 4 minutes we would pass out and we would die because there's just simply not enough oxygen. And we know that, right? There's all the scenes of if an airplane experiences an explosive decompression, the oxygen masks drop out and you have to get on oxygen quickly or you will pass out and die. And in all the movies, then the airplane dives, right, to get low enough so that the air gets dense enough so we can breathe. All right, let's go even higher. You guys remember the U-2 spy plane? This thing would fly at 85,000 feet. And then the SR-71, 95,000 feet. The X-15, the demonstrator, way high, 300,000 feet. We're still going up. How about the International Space Station? This what? Yeah, it's in an orbit that varies some, but it's like, yeah, I have 230 miles. And just recently I downloaded this Sky Tracker app so I could look and find the comet that was here. It's kind of cool. You can look around and see all the stuff, but it has an alert where every time the International Space Station flies over, it alerts me. If it's night, you know, you can go out and see that fly over. It's pretty bright. We're about done here, but how about the moon? It's way up there, right? It's averaged about 238,000 miles. So we could keep going, but that's, once you get past the moon, then you're not really, your location's not so much relative to the Earth as it is relative to the sun and where you are in orbit around the sun. Okay, so air gets thinner, so the pressure goes down, the density goes down, the temperature actually goes down and up depending upon where you are in altitude. We'll talk about that. But one of the things we want to be able to do is relate pressure with altitude. How can we calculate the pressure at a certain altitude? And so we're going to look at what's called the hydrostatic equation, where we can get a relationship between pressure and altitude that's not dependent upon measurements. It just is related to the weight of the air And that's really what causes the pressure, is the weight of the air above where you are. All right, so this is a good equation because it relates pressure and altitude. It also is an introduction to how we derive various equations in this book, where we talk about, well, we know a value at this point in the flow, and we want to calculate the value in another point in the flow, and we usually have a derivative that relates those 2 points. And in fact, then we integrate along the flow from one point to the other. So although this is not in flow, it's still the same kind of thing, as we'll get a derivative of how pressure varies with altitude. And it's the same concept. So once you understand this derivation, you'll see how the other ones work. All right, so this is the hydrostatic equation. And it relates pressure to altitude. And let's call it altitude. Let's not use a symbol. All right, so I'm going to draw a picture, and I want you to make sure you copy this in your notes. We're going to draw a box of air. And here's the ground down here. So here's sea level. And I want more room, so let me know when you're caught up here, because I want to erase this so I can draw a big box up here. Are we good? Everybody caught up? Let's see a few people still writing. All right, so at a distance h sub g above sea level, we're going to put in the middle of our box. So here's the middle of our box. Draw a box up here. So here's the front face of the box. And the box is going to go back like this, jump across that little button, come down like this. Hey, not too bad. A little wonky there in the middle, but it's supposed to be a cube. And this thing is going to be 1 meter by 1 meter. And then this is going to be a differential change in altitude. So although I've drawn it looking like a cube, we're just choosing this dimension. It's actually going to be arbitrary. You'll see how these dimensions drop out. But the height of this box is dHg, because we're going to look at how the pressure varies from the bottom face to the top face and relative to the middle. That's the middle of the box. Actually looks more like it's about here, doesn't it? So there's the middle of the box. So at the middle of the box, we're going to say the pressure is P and the density is rho. And then up at the top, it's going to increase by an amount dP over 2, because we're going halfway up the box. And then if we go halfway down the box, we're going to say it decreases by a dP over 2. And we're setting this up. We don't know what dP is. We're just saying here we know P and rho here in the middle. It decreases by an amount dP here, increases going up there. And then we're going to relate that dP to the change in altitude. So we're going to get an equation that relates dP to the altitude. And we already know it goes down, so we hope we get a negative relationship. All right, and we're also going to say the density changes, so let's write that in here next to the pressure. So the rho goes down by d rho, and up here the rho goes up. And then we're going to use Newton's law. And the sum of the forces has to be 0 because we're going to say that the box is not moving. It's not accelerating. In fact, it's stationary. Because we're looking at the atmosphere. We're not saying that the wind's blowing, the air is not moving at all. We just want to know what a static atmosphere does. So what we have to do is calculate the force on the bottom of the box and the force on the top of the box, and then the weight, because there's gravity, there's pressure force up, pressure force down, and gravity down. Oh, and by the way, we're going to say up is positive because we've designated our altitude that way. So far, so good, right? We have a box, contains air, its density is rho. We're going to calculate the mass times gravity. We're going to calculate force on the top, force on the bottom. That's easy because we know pressure. Pressure is force per unit area, right? So let's do that. So we got force on the bottom. That's up, minus the force on the top, minus the gravity. And that's equal to 0. All right, so let's work on the force on the bottom. It's going to be the pressure times the area. You can see why I picked 1 here, right? We could have picked anything, but we picked 1 meter. So 1 meter by 1 meter, that's the area times the pressure. It's the force on the bottom. Oh, wait, I got it backwards. Minus here. That's the pressure on the bottom. And then we got to subtract the force on the top, P plus dPt, times the area. And then we got to figure out the gravity. And I ran out of room, so I'm going to continue up there, but hang on a second. All right, so the reason we chose this picture is because this is our free body diagram, and the forces on it are generated by pressure and gravity, so that's what we're calculating. All right, so then we're going to continue on up here, minus this thing we're going to add here. All right, so the way we can calculate the mass is in terms of the air properties density, right? Density is mass per unit volume. So we're going to do density. Then the volume of this thing is 1 meter by 1 meter by dHg. And then that whole thing is equal to 0. So notice, compared to dynamics problems or statics problems where we're given forces and we calculate everything relative to the forces, in terms of aerodynamic properties, we have to do a little extra work to calculate the force. We need to know the area because everything's in terms of pressure. And that's because it's a gas. And we need to know how much of the gas we have. But the property of the fluid is the density, not how much mass is in this room, because we don't care about that. We want to know, well, how much mass is in whatever volume we have. And then same deal with gravity. Well, the mass is the density, and then the pressure gives us the forces. And so we need to know the area that it operates on. The upside to doing pressure is no matter what size this area is, we can calculate the force as long as we know the pressure. All right, So I think we got everything here. All right, notice that I said that the 1 meter by 1 meter doesn't really matter, because we could have called it anything we want because it just cancels out. We could have called that distance d, and then it would have canceled out. And notice we got a plus big P here and a minus big P here. So that cancels with that, because obviously the net force on this box is the difference between the bottom and the top. So it doesn't matter what the P is, it's the change in P that causes the force. And in fact, this gives us the equation, so I guess I'm moving upward here. This says dP, because we got two of them here, and they're both going to have minus signs. So the dP over 2, dP over 2 add together, move this term over to the other side. So there's a minus here, so it's going to become a plus. Did I get everything? Oh, what did I forget? Is this the force? This is density times volume, so that gives me mass, right? How do I get gravitational force out of that? I got to multiply by g. I forgot that. So in fact, we're going to flip the sign, move the minus sign over to this side just because it's easier to write. So this says if the altitude is increasing, that means dHg is positive. That means we're going up in altitude. Then there's a negative sign, so that means that the pressure is decreasing. And we know what the pressure does in the atmosphere, but we didn't include that assumption in this equation at all. We simply said altitude goes up, the pressure changes. In fact, it kind of looks like we thought maybe the pressure would be going up, right? Because we put a plus up here and a minus down here. But that's because we said positive changes up. So this equation says fundamentally that a change in altitude produces a change in pressure that's decreasing because of the weight of the air in that change. And in fact, we can integrate this from sea level up to some altitude. I'm sorry, we can integrate it from our current altitude up to all the way to infinity and find out that the pressure at a certain point is the weight of the air above it all the way out to where there's no air. Because that's what this says, is you just keep adding up each incremental change in altitude as you go up, and you can calculate the change in pressure and the net force. Yeah. Well, it's a change in altitude is related to a negative change in pressure. So you could actually integrate this equation from any point in the atmosphere upward, and what you do is add up the weight of the air all the way above it. All right, so now we go back to what we talked about a little before, a bit ago, is that the gravity changes with altitude, right? So do we include that effect here? It sounds like we have to. Because if we're going up in altitude, G is changing, and suddenly that becomes a pain. Because that looks like a nice, neat equation, and here we are saying if we plug in that formula, so now I've plugged in for absolute altitude here, the radius of the Earth plus h of g. So now we've included the dependency of gravity, g0, on altitude. Now the equation became more difficult because now we got this squared and we got h sub g down here. So if we wanted to integrate this over dh, this becomes a lot harder, right? So people said, that's too hard. Let's define a new altitude. And it assumes g is constant at g0, and we plug in g0 up here. So we throw away this thing and we say dp So is this equation right? Is it 100% accurate? No, because we said we're going to define this. Oh, we have to make this dH now because we said this. So we're saying, okay, an altitude calculated from pressure, assuming gravity. So we've really assumed, sorry, here's the word. We assumed this. So the accuracy of this thing depends upon how accurate that assumption is. Geopotential. Bad writing, geopotential. So like a lot of things we do in this class, we'll make assumptions to make things easier, and then we need to validate when is that assumption valid or not. It turns out that this is not a big deal as long as we're below like around 50 or 60,000 feet. But then once you get up to a certain altitude, G starts varying a lot more because of this formula. So really it comes down to how much does this vary as we go up in altitude, and it turns out you can go about 50 or 60,000 feet and you're still good. Now in the appendices, this is A and B, it will list both H and H sub G, and the value that I want you to use is the accurate one because it's there. We have the information. But I just want you to be aware that some calculations or examples might use the geopotential altitude. But as long as we have the tables and we can calculate this, then we just use this. Here? Well, I remembered wrong. I was way off. Scratch this. I should read my notes. It's not 60,000 feet, it's 60 kilometers. So you can go up really high before it starts getting really bad. How are we doing on time? I guess I can look at the computer, 1:09, so we got about 11 minutes left. So let's take a minute. Any questions on the homework? Most of that's pretty straightforward, right? You just use the ideal gas equation, make sure you watch your units, and punch the numbers right on your calculator and you're good. All right, there's another device that's related to this kind of thing where the weight of a fluid is supported by a pressure difference. And it's a device that we still use in our lab to measure pressure. It's called a manometer. So if we have a glass tube or a container here where we have a pressure P2, then we have another container here where we have a pressure P1. We connect a tube that is connected to those two different pressures like that. So that's a tube. It can be a hose. It needs to be clear because we need to be able to see the fluid inside it. But it could be a plastic hose, which is what we use in our lab, or it could be a glass tube, some kind of hose. And then we put a fluid in here. So this is a gas here. This is a gas here. And in here we put a fluid. And it can be any kind of fluid. Let's say, for example, an easy one is just water. But it has a density rho. All right, looking at this picture, you know there's a pressure there, there's a pressure there, there's some kind of liquid here. Which pressure is higher? You got to be able to figure this out. If I said bet $1 million on which one's higher, whether you're right or not, you should guarantee that you get it. Which one's higher? P2 is higher because you look at this and you go, if their pressures were equal, these levels would be equal, right? Oh, by the way, you have to have gravity acting here. And so really what's happening is, this is not altitude, but we still call this H. What's happening is that the pressure difference supports the weight of this piece of fluid here. Because if the pressures were equal again, the levels would be the same. So the pressure difference between the top here and essentially the bottom, because this fluid transfers the pressure from this face around to there. And so there has to be that balance. So we can, in fact, write the force balance for this is that, oh, by the way, the area of this tube is A. So that's the cross-sectional area. So the force here, P1 times A, plus the weight of that fluid times gravity has to equal P2 times A. And then the mass of the fluid, we'll just calculate from the density of the fluid. So it's going to be the density of the fluid times the area times H, because that's the volume of that piece of fluid. The cross-sectional area times the length, and that's going to give us the volume. And notice that again here, the area of this tube really doesn't matter because we're dealing in pressures and densities. So you can see another benefit to making pressure and density the variables that we need to talk about. Because the area cancels out, and this says P2 minus P1 is equal to rho GH. That's usually how it's written. People say this is the manometer equation. It's difference in pressure is rho GH. Make sure that when you do the rho here, you do the rho of the fluid, not of either of the gases. And so what this means is that you can use this as a device to measure pressure difference. In fact, you can say open this side up to atmospheric pressure and then put the other end of the tube in a wind tunnel next to your airplane, and you can measure the pressure in the wind tunnel next to the airplane relative to the atmospheric pressure. And in fact, that's what we do in a wind tunnel. And you'll do that when you get into the experimental methods class. You'll read pressures on a manometer bank that's fluid levels. So the big challenge that a lot of students face when they're using this equation is, well, I got to remember what's P2 and what's P1. And I say, don't worry about it. Because you know that this height has got to be positive. So you make sure that the P2 is the biggest one and P1 is the smaller one. And you'll get right. Otherwise, you'll end up with a negative H and it just gets messed up. So this is the clue. Just make sure that this is the biggest pressure and this is the smallest. No matter what the picture looks like, you put P2 on the side that is pushing the fluid up, and then the other one becomes P1, and it all works out. All right, I'm going to save the example till next time because it's going to take longer than the 3 minutes or 4 minutes we have left. So remind me that I still need to do the example, or we'll put some numbers in. Any questions about anything? Yep. Sorry, I'm going to have to walk over here away from the air. About what? Yeah, you should have it worked by Wednesday, but you turn it in on Friday. On Blackboard. Yeah, on Blackboard. All right, that's it for today. Thanks.
Did we just go over chapter 2 last time?
Yeah.
Okay. I had to leave. I had a 2-hour drive.